then, very scary voice. Yes. So we are, for the next hour or so, we are running the instrument. The instrument is running on its own. We don't have to do very much. So this is a great time to do introductions. And I'm so happy to be virtually present in your school in Harare. It is very special for me. I've never visited Zimbabwe, but I think that will change sometime soon. And I'll come visit you in person. But for now, this is terrific. Tony, we are recording this session on Zoom. I hope you're okay with that.
Yep, totally fine with me. Thanks for checking.
Thank you. I can tell you that when I was in school, I was never as well behaved as you all are right now. I would be chattering with my friends and making a lot of noise. So thank you for being so patient and disciplined. So Knowledge, please take it away. I'll let you do the introductions, and then we'll of course be happy to introduce ourselves whenever the opportunity comes, but I'll take off my mask for a second so you can see what I look like. That's me, I'm Raja. But Knowledge, please take it away.
So, can you hear me?
We can.
Yeah. So for the intros, so we are joining Professor Raja and his team working with the telescope this afternoon. So Professor Raja, the professor and chair of the Department of Astronomy, Astrophysics at the University of California, Santa Cruz. So I won't say much intros, but here's how the session is going to be like. So we will play guitars and get some spectra, then we'll be taking some breaks then we are going to have some species from Ruvarashe and Nokutenda Sauron. So Nokutenda and Ruvarashe became the first African to participate in a program called the Science Internship Program at the University of California, Santa Cruz. So their research project. So it was a 10-week program working with professional scientists. So their work involves astronomy. So we are going to hear from them and make some tips. Let's say you want to participate for 5 years from now. For those who are at school, so maybe you might want to participate in the program. You will get some tips and experiences from Ruvarashe and Nokutenda. And I was also, maybe we can, because part of their work, I was watching a video called We Are Stardust. They were on, and I thought maybe if time permits, we are going to play that short video as well. And because we'll be working with stars today, I think that video on Stardust, that We Are Stardust, will have a great impact on us. I think that's all I can say, Professor Raja, and your team. Maybe yes. So over to you. Thank you.
Knowledge, I missed the last part of what you said. Did you want us to introduce ourselves? Carlos, let me take this opportunity to ask. Okay. We are trying to change the display on Magic.
To show the guider image?
Oh, okay. Yeah, so what you need to do, yeah, that's a bug on the software. So it keeps showing the image from the previous instrument. So what you want to do, actually, the way to sort that out is you just need to exit that Magic GUI and start a new one.
Okay.
So go ahead and just destroy.
Destroy.
Wow.
And now right click, and it's under telescope GUIs. And then is the magic guider user interface. Yeah, and now is it so the DEIMOS guider.
And one of the things we can do very easily is I can share my screen so you can see what we are looking at over here. Okay, I will do that. And then I can also turn off my screen share for when we are introducing ourselves. So I'm sharing my screen. You can hopefully see these. We are using 4 display windows. This is 1, this is a 2nd, this is a 3rd, and this is the 4th. And what you're seeing in this image on the left, upper left, is you are seeing images of the sky. These are actual stars for which we are taking images in real time right now.
Raja, I'm sorry, can I interrupt you?
Of course.
Because all I'm seeing is a black screen, so I'm not entirely sure if everyone can see your screen, because I can't.
Really, even now?
No, yes, I can, Tony, I think that's because you're using a polygon.
Ah, okay.
And it's not very good
Okay.
with sharing a screen, but I have my laptop here and I can see the screen sharing from Raja.
Okay, so sorry to interrupt. I just
No, not at all. I'm glad you brought it up.
help.
I'm really glad you brought it up. That's good to know. I'm going to share our video panel so you can see who we are still. Hopefully you can now see both video and our screens, Carlos.
That is affirmative.
Okay, thank you. That is very military of you to say affirmative. Okay. So, Knowledge, would you like us to introduce ourselves? I'm sorry if you already told us, but I didn't hear.
Hi, Raja. Yeah, you can go ahead and introduce yourself.
Okay, so I think the first introduction should come from Amanda, then Carlos, then Tony, and then me. Okay, so Amanda, please take it away, and if you need to, I have to move away.
Okay. Hi, everyone. I'm Amanda. I'll quickly show you what my whole face looks like. I am Raja's graduate student. So that means after grade school, I went to college, and then I decided I wanted to stay a student for a couple more years. So now I'm in graduate school, getting my PhD in astronomy. I study the galaxy that we're looking at. It's called Triangulum, and it's a close by galaxy that sometimes you can see in the sky if it's very clear, but with this telescope, we can really zoom in on it and look at individual stars. And we'll talk about that later tonight. In my personal life, I really like to snorkel. So I'm extra grateful that I get to use a telescope in Hawaii, where I get to go swimming in the ocean with some fish. And after graduate school, I really want to teach. So that's my goal after getting my PhD. Okay.
Thank you, Amanda. That's terrific. Carlos, it's your turn.
Yeah. So yeah, hi everybody. So yeah, my name is Carlos. I'm actually originally from Spain, but I've been working here in Hawaii for the last 6 years. And my role here, I am tonight the staff astronomer. So what my job consists of is just to make sure that the observations that Amanda and Raja are doing tonight are successful. So I am the instrument scientist for the instrument that they are using tonight. So if they have any issues when they are doing the observations, if the instrument does anything weird or misbehaves, I help with troubleshooting together with Tony, who is on the summit. Yeah, we together help troubleshooting any issue that might happen during the observations to make sure that we optimize the observing time through the night. And yeah, so before, well, I've been working in astronomy for many years, more than 20 years. And I actually didn't study astrophysics initially. I studied solid state physics, but I always wanted to do astronomy. So after I finished my degree in solid state physics, I went back to school and did astrophysics. And after that, I did a PhD in the UK, in Leeds in the UK, and also worked for 2 years as
CCD readout complete.
As a postdoc in the Max Planck Institute for Astronomy in Heidelberg. And then after that, I was working in an observatory in the Canary Islands in Spain for 10 years as staff astronomer before moving here to Hawaii to continue the same line of work, also as a staff astronomer, but in this case for the Keck Observatory. And well, things that I like to do in my free time when I'm not working, I like a lot to do trail running. So I like running and cycling and swimming, but especially running is one of my favorite things to do. So Tony, I think it's your turn.
Yes, thank you, Carlos. Hi, everyone. My name's Tony. I am a observing assistant here at Keck, which means I am I'm the telescope operator. So I'm the one working physically up on the mountain. In fact, the telescope is behind the wall behind me. My role here is running several systems of the observatory to make sure that the observers are getting the science that they need. So I do the slewing, the moving of the telescope around the sky, making sure the telescope is focused. Like Carlos said, we troubleshoot issues as they come up. I check the weather and make sure that it's safe to be open and not raining or snowing on the telescope. So things like that. It also means, like I said, I'm physically up here at the telescope, which is one of my favorite aspects of the job. Being up on the very top of the mountain is such a cool experience. I've seen who knows how many, beautiful sunsets and sunrises out here. I've been working at Keck for 4 years. I've done the same job operating the telescope at a couple other observatories before I moved here at Keck. But I've been living here in Hawaii since I was 18. I moved out here to go to college at the University of Hawaii at Hilo, and basically never left. I'm originally from the state of South Dakota, which is basically right in the middle of the United States. So I moved a very long ways away from home, and I'm still here. So yeah, it's a little bit about me. I'll give it over to you, Raja.
Thank you. So Tony is actually the only one among us in this Zoom call who is on a mountaintop right now. I don't know if you heard that. Carlos has a picture of that mountaintop behind him, but that's a virtual background for him. And for Tony, that's the real background. If Tony could go outside, he would see something very similar to what Carlos is showing in his virtual background. So Tony's actually on a mountaintop whose height is, in meters, it would be
4,200.
4,200 meters, 4,200 meters, almost 14,000 feet. This is the summit of Maunakea, the sacred mountain of Maunakea. Maunakea means white mountain in the Hawaiian language, and it's been a sacred mountain for the Hawaiian people for many years. and we have the privilege of using that mountain for astronomical observations. It's one of the best sites in the world to carry out optical infrared observations. And so I don't know if you heard that before, but Tony is really on that mountaintop. And Carlos, Amanda and I are in the same room. Carlos is one room over. We are at the headquarters of the observatory, which is only at a much lower altitude. It's only about 600 meters, the altitude. It's right, Carlos, a little more than 600 meters. It's about 2,500 feet.
It's nearly 1,000 meters, a little below that. Not
oh, below 1,000 meters.
800 or so.
800 meters. Okay, that's the altitude of Waimea. Carlos, that's the
that is correct. That's Waimea. Yeah.
Waimea. Okay, so we're in the town of Waimea, which is on the main island of Hawaii, what is called the Big Island of Hawaii. The state of Hawaii has many islands. The biggest island has the name of Hawaii also, so it's often referred to as the Big Island. That's where we are. So like Amanda, I live in California, and I have come to the island of Hawaii just for a few nights to carry out these observations. Now, I'm sharing my screen, so hopefully you are seeing knowledge or someone from Harare. If you could please confirm that you're seeing my screen. When I move my cursor, do you see that we are seeing this, what looks like half of a bell curve? Do you see that? Are you seeing that in Zimbabwe? This where we're trying to make a measurement of how sharp the stellar images is. Can you see that? You can please confirm you can either confirm by chat or by voice, whatever works best.
Confirm, we can see.
You can, okay, excellent, excellent. So I haven't introduced myself. I've taken off my mask for a few seconds here. My name is Raja. I'm a professor at UC Santa Cruz, as Knowledge mentioned. I've been coming to Hawaii for over 25 years. This is very close to my 26th anniversary of the first time I used the Keck telescope. Carlos, you found that date for me. It was 16th September of 1995. I was using not this telescope, I was using the Keck I telescope. The Keck II telescope wasn't in operation for one more year, I think. Keck II went into operation, I think, in 1996, if I remember correctly. Anyway, I was using the Keck I telescope and a different instrument called LRIS, Low Resolution Imaging Spectrograph. Tonight, we're using an instrument called DEIMOS. Those are the details you're seeing on the screen. DEIMOS is a different kind of camera than LRIS. It stands for Deep Extragalactic Imaging Multi-Object Spectrograph. I'm going to write this in the chat. DEIMOS equals Deep Extragalactic Imaging Multi-Object Spectrograph. This spectrograph was designed and built by one of my colleagues at UC Santa Cruz. She's a very famous astronomer. Her name is Sandy Faber. And the spectrograph is the size of a small room. I've climbed into that spectrograph when it was being built at Santa Cruz. So it's several feet by several feet, or a few meters by a few meters in size. It's shaped like a cylinder, shaped like a giant cylinder. That's the overall shape of the spectrograph. Its task is to take the light from the telescope, and after the light has come into focus, it goes into that spectrograph, and using something like a prism, it breaks up the light into the colors of the rainbow. And we take a spectrum with that, and in a few minutes, we'll show you the details of some of the spectra that Amanda and I have collected tonight. So what I'm doing, can you still hear me through my mask? Is that okay? Carlos, can you hear me okay? Okay, great, thanks. What we're doing here So I just put in the chat the name of the spectrograph, DEIMOS, and the chat is going to be recorded as well. So we should be able to see when I send the recording to all of you, I'll send the chat also. So I know that Noku and Ru were going to introduce themselves. Is this a good time to do that for them? Because we are okay with them doing that. We're not doing anything special with the instrument right now. We are waiting. In fact, I can show you that we are, if I go to this screen, you can see that we are taking, where it says integration, in parentheses seconds, we are taking an integration that's 1050 seconds. And if you do your mathematics, you'll see that if you divide this by 60, this is 17.5 minutes. If you take 1050 and divide by 60, you get 17.5. So we are taking a 17.5 minute exposure. And during that time, really, we don't have to do very much except make sure that the instrument is not malfunctioning. So 17.5 minutes. Out of these 17.5 minutes, 600 seconds have already passed. So 10 minutes have passed. So we have about 7.5 minutes left, little less than 7.5 minutes left to go. So, but even after the 7.5 minutes finishes, you'll see that we will type a command and we'll start a sequence of 3 more 17.5 minute exposures. So we have nearly an hour left if you want to do introductions from Noku and Ru. Is this a good time for them to introduce themselves, Knowledge? And Knowledge, I realize you haven't introduced yourself while we've been recording. So please introduce yourself next. There's Knowledge. Okay.
Hello.
We can hear you fine, Knowledge.
Yeah, I'm sorry, I just got out. Yeah, for the intro, yeah, my name is Knowledge. I am the founder of the Africa Science Masters Festival. We work with primary and high school students promoting science through science shows and teacher training workshops. So we have a program we call the Science Seekers, which is a traveling exhibition where professional scientists perform science in public places using everyday materials. So between 2017 and 2019, we engaged over 100,000 children and teachers in Zimbabwe, Zambia, Botswana, Malawi, and in South Africa through our science shows. And we do have an annual event called the Africa Science Masters Festival, where high school students demonstrate or showcase their research works and science communication projects. Yeah, so I spent time working with schools, children, and teachers. And it's my great pleasure today that we are joining you from Harare with a team of, with a group of 45 students from 3 primary and high schools. I think that's, I'm not sure if that's enough for it, but.
Knowledge, can you give me the names of the countries one more time? You said Zimbabwe, Zambia, Malawi, and South Africa. Did I miss any countries?
Botswana.
Botswana, okay. And you said 100,000 students and teachers between 2017 and 2019, right?
Over 100,000.
Over 100,000. That's impressive. That is so, so impressive. I'm just putting this into the chat because this way it will be recorded. Wonderful. No, you're doing amazing work, and I'm so privileged that you and I got connected last summer by Anika, and I was privileged to speak at the Africa Science Buskers Festival last summer, and this year I was even happier to see Noku and Ru as keynote speakers in the Africa Science Buskers Festival. So is it their turn to introduce themselves now, you think?
So Ru and Noku, right?
Yes.
Yes, so yeah, they are here.
Good day.
Hello.
Hello, everyone. So my name is Natasha Moyo. I'm a grade 8 student at Queen Elizabeth High School in Harare, Zimbabwe. I'm a young scientist who's ready to bring sustainable development in my community. I'm the co-founder and CEO of Genius Space Explorers, a company that seeks to improve lives, inspire, and bring curiosity to children through space exploration and astronomy. So I'm very excited to be joining you today in observing the stars. Thank you.
Hello, everyone. My name is Katenda Sarah. I'm from student at Queen Elizabeth High School in Harare, Zimbabwe. I'm the co-founder of Genius Space Explorers, a company that aims to improve life and inspire and to feed curiosity in young people through space exploration and astronomy. I was an intern at the University of California, Santa Cruz during the summer for this year in 2021. And I'm so excited to be part of this Keck II 10-meter observatory station. Thank you.
Thank you. That's terrific. I've just put this into the chat. Ru and Noku are from Queen Elizabeth High School in Harare, Zimbabwe, and they're the founders of the Junior Science Explorers program. And so they're actually collaborating with one of my colleagues, Professor Nia Imara, and myself on a project to bring a do-it-yourself radio telescope project to school students first in Harare, but then hopefully later to other students in other parts of Africa as well. Ru and Noku, do you want to say a little bit more about your experience at Santa Cruz this summer, a virtual experience?
Yeah, so it has been a great opportunity to be intern at the University of California during the science internship program. We got an opportunity to learn the basics of astrophysics concepts such as the spectra, its dynamics, and also we got an opportunity to learn the basics of Python computer programming via a series of 6-computer notebooks. So we participated in a science project called PR Studies in collaboration with Keck Art and Culture. So during the 10 weeks at the science internship program, we worked with our mentors, faculty advisors, and other interns around the world.
So as Messier, we got interns at SEEP Messier. So it was an amazing and life-changing experience for me because I learned a lot of things like science communication. We're working on a research project called We Are Stardust. So this was a connection of art, STEM, and culture where we're making 3 stories in connection to the stars. My story, science story, and culture story. Hopefully at the end of the break, I'm going to share with you a part
CTD
of the
readout
that
complete.
I made. Also, I really had a great time working from all around the world and working with professional professors in the field of astronomy, and also getting a chance to interconnect our culture and astronomy.
That is wonderful. Thank you. So what we are doing here, I'm sharing my screen with all of you. So you're seeing the operations of the Keck telescope and DEIMOS spectrograph. What Amanda is showing us, she's adjusting the contrast and brightness of this screen.
She is struggling to adjust the contrast.
I'm happy to show if you want.
Yeah.
Amanda,
Yeah.
Amanda, it might work a little bit better if you use, instead of 50,000, you use something like maybe 2,000 counts.
Okay.
How many? 2,000. Okay.
Yeah. So hit cut levels now. You need to hit cut levels. Yeah.
Right.
And now give it a try again. Probably will work better. And instead of doing, if it doesn't respond very well, just do it at small steps, and I'll work a little bit better.
Okay. Thanks, Carlos.
No problem.
Yeah, that looks much better.
This is beautiful. So I'm going to zoom out first. And I think this is a good time to transition to talking about the experiment we are doing. So as Amanda mentioned, we are studying a galaxy that is smaller than our Milky Way. And it is in fact a family member of the Milky Way. It is similar to the Milky Way. It's like our cousin. It is smaller than the Milky Way, but not, it still has the same basic structure as the Milky Way. It has a disk, and it has what we thought it only has a disk, but it has more than that. Let me see if I can show you a picture of this galaxy. Just give me a moment.
Do you have Keynote, Raja?
I don't. I do have Keynote.
Okay.
Here.
Do you want me to send you my Keck PowerPoint?
We can do that, or if you wanted to share your screen.
I'm not on Zoom and I'm not set up for the VNC.
No
Oh,
problem.
I could join the Zoom though.
You could join the Zoom.
Okay.
Yeah, you could just join the Zoom
Yeah.
and share your screen. I'll stop sharing for that. And I'll turn off my sound, etc. So what we're going to do is Amanda is going to give you a little introduction about the experiment we're doing, and I'll turn off my my sound for that.
So something that I've noticed, Raja, is that if what you have on the upper right is your chat window, on my, at least on my Zoom, that one doesn't show really any information. It's like a gray box. So I couldn't see any text embedded in it. Just letting you know. I don't know if that is happening elsewhere, but definitely I don't see any text in there at all.
Yeah.
I see, it shows up like that, I see. So if you click on the, I'll close it, but if you click on the chat box yourself, you'll see it.
Yes, if I do that, I'll see it, but I guess it won't work for the recording though.
Right, I've closed it, but we are recording the chat separately.
Okay.
But now it should have gone away because I closed the chat box.
Yeah, now it's not there anymore. It's only the video and the DEIMOS DNC.
So I'm going to zoom in a little bit so I can show you what the spectrum of an individual star looks like. Let me zoom in some more. Some stars, we'd start with a bright star like this one. Quickly. For the students in Harare, you should be able to see that there are many horizontal lines like this. And each horizontal line is produced by our Earth's atmosphere. The atmosphere is glowing, and it produces these horizontal lines like this when you see the atmosphere through a slit. I'm going to go get a slit mask. I can show you what it looks like. Carlos kindly lent me one. So let's see. So I don't know if you can see, but this metal plate that you see here, we look at the sky through one of these metal plates. And you can see that the metal plate has some cuts in it, rectangular cuts. You can see that. This is a long rectangular cut right over there. There are some short ones. There are some squares cut like this. I hope you can see. So we look at the sky through one of these plates, and each of these cuts produces a vertical band like this. Okay, a vertical band running from where we are measuring the spectrum of distant objects, distant stars inside this galaxy that Amanda will talk about next. Okay, so I will stop my screen share and hand it over to Amanda now, and I will turn off my sound.
Okay, I have my sound up now.
Okay.
Okay. All right, hi everyone. If you can hear me, I'm gonna show some pictures of what Raja was talking about. So first, I'll just show some pictures of Keck, and then I'll talk about the galaxy we're looking at. Okay, so as Raja, Tony, and Carlos talked about, we're in Hawaii, and the mountain that the telescope is on is named Maunakea. And this is a map of the mountain. It's very tall. And it's so tall that you're above the cloud layer. So when you go, it looks almost like you're on Mars. So you're looking down at clouds. The rock is brown, red, and lots of rock and gravel. So it's what I imagine being on a different planet would look like. And it is amazing. So it's nice and warm in Hawaii on the beach, but this mountain is so tall that it will snow on the mountain. As Tony said, he has to sometimes close the dome so that snow doesn't get to the instrument, which seems funny when we're in such a tropical place. So there's more than just the Keck telescope on Maunakea, and this is a map of some of the telescopes, and then I have actual photos. So here are 3 telescopes called the Canada, France, Hawaii telescope, Gemini North, and then a telescope run by the University of Hawaii. These are all on Maunakea, and then you can also see the road to drive up to the observatory. I just like this picture. Again, you can see the clouds in the background, just slightly below you. You are at cloud level or above them. And then we have a view of the telescopes we're using. So Keck I and Keck II are twin telescopes. The telescopes themselves are twins, so very similar, but they have different instruments on them. So not only does it matter what telescope you're using, but it matters what instrument you're using. And Raja mentioned that we're using the DEIMOS spectrograph, and I'll talk a little bit about that in a moment. Keck I and Keck II are connected by a building, so you can walk between them. And then there are two other telescopes near the Keck telescope as well. And in this photo, you can see the color of the landscape a little better.
Amanda, did you take these pictures yourself?
I did. I took these pictures.
That's amazing. That's amazing. They're wonderful photos.
Thank you. I visited the summit once a couple years ago. So some facts about Keck I and Keck II. They're both very large. They took a while to build because these are massive facilities. And the bigger the telescope, the more money it costs too. It takes a lot to run these giant telescopes. So there are just rooms of data storage computers. So where all of our data goes on. And then there's a lot of electricity and circuit boards that goes into these telescopes as well. I am not an engineer, so I don't really understand any of this, but it takes a lot of work to build these really complex instruments, and without them, astronomy wouldn't happen. So it's really important and really fantastic that there are people who work on instrumentation, who build and support these instruments so that we can learn anything about space, because without them, we would not be able to. The Keck II telescope, it's really hard to see from this image, but it's 10 meters across, which is just over 30 feet. So if you start at one end and went across the mirror, that's 10 meters. So it's very large. This also weighs a lot, 37,000 tons. I'm not sure if that's a unit that anybody around the world uses other than the US. But that's very heavy, and that's amazing because we have to be able to move this telescope precisely to point at our patch of sky. So the fact that it's been engineered, it's actually floating on pressurized oil so that there's very little friction when they move the telescope. Because the mirror, the collecting area is so large, it would be a really fragile piece of glass if it were just one piece of glass to make the mirror. It would also not be very stable and would be very hard to make. So instead, there are 36 mirror segments. They're all hectagons that fit together to create the very large mirror. And this is the photo on the right is the back of one of these mirror segments. And these mirror segments can be slightly deformed so that they all fit together perfectly. So it's like it's one mirror. Also, Tony and Carlos, if I say something at any point that is wrong, please feel free to correct me. I am definitely not the expert here. So we've mentioned a couple of times that we use the DEIMOS spectrograph. So I just want to briefly say what a spectrograph is. So when you take a picture on your camera, you're doing something called photometry. You're collecting the photons or the light that comes from whatever you're taking a picture of, and then you're not doing anything with that light. With spectroscopy, we want to spread the light out so that we can see what that light is telling us about the star. So using a spectrograph is like we're putting the light of a star through a prism. So it starts as white light from the star, all of the colors combined. And then when it goes through this instrument, which is much more complex than just a prism, but it's the same idea, it spreads the light out into a rainbow. So we can now see the red light of a star, how much blue light, how much purple light is in the star. And that tells us a lot about the star. Stars actually give away all of their secrets through their light. So we can figure out what kinds of chemicals or elements are in a star. We can also, through a technique called the Doppler shift, figure out how fast that star is moving towards or away from us. And that's the thing that I care most about, how the star is moving. And so if you've ever heard a siren on a vehicle before, you might have noticed that when the vehicle is coming towards you, the sound is a higher pitch. And then when the vehicle goes away from you, the sound becomes a lower pitch. And there's nothing that changed about the actual sound. It's just an effect of the sound waves squishing up against each other when the vehicle comes towards you, and then being stretched out as the vehicle goes away from you. Since light is also a wave, it also is affected by this Doppler shift. So we can use that to tell how fast a star is moving towards or away from us.
Amanda, if you could go back to the last slide for a minute. I love this diagram over here on the left. The green elements, one represents the primary mirror of the Keck telescope. In Keck, instead of using lenses, we're using mirrors. So this first green one is, instead of a lens, is a mirror. And the second one, I think the collimator is also a mirror in the case of...
yeah, this is not a picture of DEIMOS. This is just an example.
It's a wonderful illustration, though, of what happens. The telescope focuses the light. It goes through that slit. That line that's marked as slit, that was that method I was holding up for you a few minutes ago. And once it goes through that, it hits another mirror that takes a divergent beam and makes it parallel. And then the rest of it is actually done with lenses, not mirrors, just as shown here. Sorry to interrupt.
No, that's great. Thank you, Raja. And so you might think that prisms are very small, but DEIMOS is quite a large instrument. I got to meet DEIMOS when I went to the summit. And so we can't actually see the instrument because it's housed in this casing to keep it safe, and so that it doesn't pick up any light from the observatory or any dust or anything like that. But it's very large. And so this is the galaxy that we're looking at. This is a real image of the Triangulum galaxy. It's also called M33. So if you hear us say Triangulum or M33 tonight, we're talking about the same galaxy. It's a spiral galaxy, which I think are the most beautiful kind of galaxies because you can see the spiral arms. They have more color from dust and star formation going on. But it's a less massive galaxy than our own. It's in our galactic neighborhood though, so it is our neighbor, 3 million light years away. So it would take light 3 million years from the galaxy to get to us. That means we're seeing this galaxy in the past, which is a really crazy concept to think about. And it's the third largest galaxy in our galactic neighborhood.
That was good. This one was very good. The update was fine.
And so when we observe M33, we have to decide where we're going to point the telescope. There are billions of stars in this galaxy, and unfortunately, we can't observe them all. So we have to target specific stars. The green rectangle on this image is about the size of a DEIMOS mask. So when we point the telescope, this is the area we can see at a time. And since M33 is a smaller galaxy, it's actually very convenient. We can observe the entire disk of this galaxy with 1, 2, 3, 4, 5. So we can look at the inner disk of this galaxy by stacking 5 DEIMOS masks on top of each other. So we'll point the telescope at the top position. We'll observe stars between 1.5 and 2 hours. We can look at about 150 to 200 stars at a time. And then Tony moves the telescope for us to the next position and we look at new stars. Raja showed you a slit mask. So this image is less exciting than the actual metal plates, but you can see it's not quite a rectangle. I was just using rectangles in the past image because that's a little easier to make on diagrams. So this is the real shape of the mask. And what we do is we design this mask on the computer. So this is a screenshot of me designing one of the masks, with a program called DSimulator. So the yellow outline is the real shape of the DEIMOS mask. And then all of the little lines you see here are potential stars that we could look at. And so the red stars are ones that are not on our mask. And then the blue and green ones are ones that fit on our mask. But we can't put all of these stars on our mask. So this program helps decide which stars we care about seeing most. And once we design this mask, we send it to the observatory and they make it for us. So they have a drill at the observatory that drills the little slits and the alignment boxes according to our plan into these pieces of metal. And once they have the masks made, we tell them which ones we want to observe on which night, and they load them into DEIMOS so that during the night, we can just change masks based on what we want. Okay, I'm gonna momentarily stop sharing my screen and share one other slide, and then I will stop talking because I'm giving a lot of information at once. So I showed a really old image of the survey area, but Raja had and I have a lot of fun with this. So we've been looking at M33 for so long, we've created a survey. So a large data set of observations of this galaxy. So when I showed you the image on the last PowerPoint, it only had these green rectangles, these green inner ones, which we observed in 2018 and 2019. But we had some older ones from 2016 below the green. And then last year, we went farther out into the galaxy with these red masks. Today, we're looking even farther, so off of this image. But we named this survey, this data set, the T-Rex survey, which stands for the Triangulum Extended Survey. Because when you turn this map into a map that shows actual stars, so on the right image, every little dot here represents one of the stars that we have observed in M33.
And they're color-coded by velocity, right?
Yes.
Wow.
And so Raja and I thought that this looked like a dinosaur. So we named it the T-Rex survey. This is the T-Rex. You might disagree that this doesn't quite look like a T-Rex. And after some searching, we found that a dinosaur called the Parasaurolophus was the best fitting shape for this map, but we could not figure out how to get the name to work. So we stuck with the T-Rex survey, even though it's not the correct dinosaur. But we are astronomers and not paleontologists, so we're sticking with it.
But this has really become part of our lexicon. So sometimes we say, let's look at the femur bone of the dinosaur when we want to talk about those stars, or let's look at the head of the dinosaur when we want to look at those stars. So we have started using this terminology within our team. We really think of it as a dinosaur.
And this observing run, we filled in its belly. So there will be stars now around the center where you can see there's a gap. So our dinosaur just becomes more and more complete. It also is going to have a top hat after we observe this run. So we're really committed to the image of a dinosaur. Okay, I'm going to stop sharing my screen. That was a lot of information and not a lot of time. So if you have questions, please feel free to ask. If something didn't make sense, that's totally fine. I'm happy to try to re-explain. Yeah, it was a lot of information.
That was fantastic. Oh, can you hear me now? Okay.
Yes.
Any questions? I see. Carlos, 370 US ton is 335 metric tons. I see. And a metric ton is 1,000 kilograms, is it?
That is correct. Yeah. 1,000 kilograms per metric ton. The other thing I was going to say is that those, just to get an idea of the scale on those slit masks, the dimension, the size of the slit mask horizontally on the sky is about half the diameter of the full moon. So that gives you an idea of how large M33 is actually on the sky. It's bigger than the moon.
Yeah, that's true. So the DEIMOS mask is about the radius of the full moon. And
no, yeah, exactly. That is correct. Yeah. 15 arc minutes. Yeah. And the moon is half a degree, which is 30 arc minutes. So, yeah, but M33 is bigger.
Yeah, the overall area we are surveying is somewhat bigger than it's several full moons across on the sky. Any questions at all, really, from the group? How many students are in the room? And tell me, is it 2 o'clock in the afternoon in Zimbabwe now, in Harare? Oh, yes, knowledge. This is a great time to do that. You're in.
Yeah, Raja, it's, can you hear me?
Yes, we can hear you fine.
Yeah, it's 2 p.m. In the afternoon. So I will, yes, we can, because Ru did a wonderful video during the SIP. So I'm going to play it now. Okay, so I will play it now. Let me share my screen.
Let me know if you're able to share your screen. Otherwise, I will make sure you have permission. Knowledge, are you able to share your screen?
Just FYI, Roger, we have 6 minutes left in this exposure and then we are going to move.
Got it. So knowledge, it looks like in the next 6 or 10 minutes, well, in the next 6 minutes, after 6 minutes, we will have to make an instrument change. So we may have to, it may be better to wait to change the parameters of the instrument in 6 minutes. And then we do the video if that's okay, because I don't want to interrupt the video.
Sure, that's fine. That's fine. Yeah.
But your screen share is working now. So I may take the screen share back from you so you can see, so the students can see what we are doing.
Sure. So I will stop.
Okay, yeah, okay. So we have our screen share back. And let me just make sure sorry to interrupt what you were about to do. So I'm going to share my screen briefly, and it is optimized for sound. And so what we're going to do in a few seconds is we will go to, you can see that out of the 1050 seconds, nearly 800 seconds have elapsed already. The progress is showing 777, 78. So we have only about, let me see if I can do this math in my head, about 5 minutes left, because if you add 5 minutes, it's 300 seconds. If you add 300 seconds to 795, you actually get more than 10:50. So we have less than 5 minutes left, right? I wonder if I'm doing my math correctly. I have a difficult time doing math after I've been awake too late at night. But so when this thing goes to 100%, what will happen is it will flush out the silicon device, and it will give us a new image of the spectra of stars in the Triangulum galaxy. And we will be able to see that on this screen here. These are, you're seeing spectra already, these vertical streaks. You can see this vertical streak that my cursor is going down. There's another one over here, one over here, this one, this one, this one. These gray or white streaks, light gray or white streaks, these are spectra of the stars in Triangulum that we are interested in. If I move over here, you'll see a different set. I don't know if you can see this red box. It was over here before on the lower left, but now I've moved it to the closer to the middle. And you can see that every one of these bands, vertical bands, contains a streak. Sometimes it's very faint, almost impossible to see, like this one or this one, but here you can see it. Here you can see it. Here you can see it very clearly. Here as well. So you can see that many of these rectangles are successfully picking up, all of them are successfully picking up the light of faint stars, but some stars are so faint that we can't see very much in a single exposure. Each exposure, again, is 17.5 minutes. So we're about to read out the next exposure. Is it okay if I zoom in for that? Okay. I'm just going to zoom in.
I'll just tell you this.
Of course, absolutely. In fact, Tony should be able to hear you over this. So Tony, we are getting ready to move to our next target, which will be PTST 2.
And is highlighted.
Yep, I see it highlighted. Thanks.
We're ready to move in just a few seconds. We should be ready to move in now, about 2 minutes. Exactly 2 minutes now, counting down from 2 minutes. When this thing finishes, you can see it's now 89%, 90%. When this goes to 100%, the CCD will flush out, and we'll see that. I want to show you exactly what happens when it reads out a new image. So once this 955, 956, 957, off target, let's hope it comes back. Wow, it's very far off target. Yes. Okay, let's come back closer.
Yeah, that must have been a cosmic ray, I guess, because
got it. It's almost back. Hopefully in the next update it will come back.
It's gonna keep doing that every 15 seconds until it comes back.
Okay. It's very close now. It overshot. Hopefully it will come back here.
Yeah, when it gets one of these, as I say, it's probably a cosmic ray, then it tries to correct something that is not really an offset, and it takes a while until it goes back.
Got it.
Now it is back.
Good. And in the meantime, it is almost finished the exposure. So you can see 1043, 1044. When it hits 1050, you'll hear a voice saying exposure complete.
Exposure complete.
Okay, and now
I'm going to change the mask if they want to see that.
Oh yeah. So what Amanda's going to do is change the mask to a different metal plate.
Yep, I'm slowing now.
Thank you. So this thing that went gray over here in this part, it's because Amanda's requested a change in the instrument configuration. A different metal plate is being moved in where the old one was, a different mask. And we're also changing the tilt of the grating to go from first order to 0th order. The object name is also something that we will change instead of a PTH1, it will be PTST2. And that's something that will reflect a slightly...
ECD readout complete.
You could see that it updated, I don't know if you could see, but it updated the image of the spectra.
ACS is not settled.
Sorry if I'm interfering with the cursor.
I'll take over here.
No problem, you should take over. Yeah. Will we keep the same exposure?
Yeah. Depending on how fast or slow the alignment is.
All right. So it's perfectly democratic, splitting the time of mass. I think that was the right decision, and I think this is looking, with 4 of these real potential velocities for many things. Okay, but this is going to be back 1 galaxy anyway.
Okay, we're in position here and guiding.
Great, thanks.
So what we're doing now, what Amanda's doing now is first getting a rough pointing of the telescope, pointing the telescope in the right patch of the sky. And the way we do that is by grabbing an image and making a fine adjustment to it. Even this is considered a coarse adjustment, but then we'll do the fine adjustment in a minute. You can see that she clicked on the move telescope button. So it actually moves the telescope by a small amount, very small amount. There we go.
Now we have stars and boxes.
And she will start the fine alignment. The idea is in that metal plate, there are these square boxes that have been cut, and they have been cut at the location of bright stars. Amanda designed this so that if the telescope is pointed right, there should be a bright star shining through each of those boxes. And we want to make sure that those stars are really centered on those boxes before we spend an hour and more than an hour collecting light. We are spending 60-some minutes, 1050, 17 and a half.
Exposure complete.
70 minutes. We're spending 17 and a half multiplied by 4 is 17 and a half times 2 is 35. 35 times 2 is 70 minutes. We're spending 70 minutes, an hour and 10 minutes, collecting light from these stars because they're so faint. But right now, before we're doing that,
ECD readout complete.
So we are trying to make sure that the telescope is pointed exactly correctly. Wow, look at that. That's beautiful. That is really beautiful.
This all looks good. So I'm going to send moves and repeat.
Yeah. So you can see that in each of these panels, you could see just a moment ago that there were peaks, but the peaks were not centered. So we want the stars to be at the center of the box. So we've asked the telescope to make a small adjustment. It does all the calculations to ask how much does it need to change the X and the Y and how much does it need to change the rotation. It adjusts those 3 things. You can see that the X, Y, and rotation is measured in degrees. X and Y are measured in arc seconds, which is a unit of angle.
Exposure complete.
It's so it's taken a second exposure, it's taken 20-second exposures, because that's why we need bright stars, because it takes short exposures. We don't want to spend a lot of time on the alignment. We want to make that as quick as possible. So in a few seconds, you'll see these peaks again.
ECD readout complete.
So in a few seconds, you'll see the peaks, and now they're centered. They're beautifully centered.
Okay, Tony, we're aligned. You can mark base.
Okay, base is marked here.
Amanda is now going to change the configuration of the spectrograph so that it's able to now take spectra instead of images by changing the tilt of the grating. And as soon as that is ready, you can see that this is 20%, 31%. This is getting ready. As soon as that is ready, we will start a sequence of 4 exposures. And Amanda will do that by typing a command into this window over here. In fact, she's typed in the command WFFCS GuhaI4. That means WF stands for wait for, FCS stands for flexure compensation system. And after it's done, semicolon means like a carriage return in Unix. And then GuhaI means go integrate 4 times, not once, but 4 times. So it will take 4 17.5-minute exposures. And the exposure time is set over here, 1050. In seconds is 17.5 minutes. And as soon as that starts, which will start, you'll see that what is happening here is the FCS is trying to catch up, the flexure compensation system. This is the thing that corrects for the fact that we have this very large metal spectrograph, and as it changes its orientation, the force of gravity causes it to bend, and we try to compensate for that. Flexure compensation system it corrects for that. So this is a scale of 5, okay? Let's, so we want this green box to move inside this pink rectangle. Once it does that, then we know that the correction is happening properly. Right now it says off target over here, but once the green box moves inside, it will be, you can see it's moving closer. Once this is all happening automatically. Once it moves inside, this will change from off target to tracking. And when that happens, it will start, the progress bar will start counting up. Right now it hasn't yet started, but once this green box moves in here, and I can zoom in a little bit to show you. In a moment, I will zoom in. Once the green box moves a little closer, I will zoom in. There we go. You can see that it needs to move a little bit closer, and then it'll go from seeking to tracking. So we have to be, as astronomers, we have to be very patient. This thing takes some time, but it's also important for the telescope to be just right before we start taking data.
Overdid it.
It overdid it, but it's going to come back. Clear samples and go out one more time. We want to really come inside here. And for that, we need one more move, I think, and it will be ready. Yes, wonderful, wonderful. Now you see it says tracking instead of off target or seeking, it says tracking. And now the progress bar has changed from 2 minuses to it's now counting up. So this is the exact start of collecting photons. And as Amanda said, these photons, these particles of light that are coming to us have been traveling for nearly 3 million years. They've been traveling. So this is a very good time for me to stop sharing my screen and to hand you the screen share again knowledge. And I will turn my sound off.
Thank you, Raja. I'm really enjoying this. Thank you very much. So I will now share the We Are Stardust production by Ru Varashimuyo. So
we are not getting the sound. So if you want to do share with sound, that would be better.
So it doesn't have sound.
Oh, it doesn't have sound. Okay, no problem.
You mean you can't hear the sound?
No, we can't hear the sound. So what you have to do is if you stop your screen share and start again, in the bottom left of the screen share, it gives you the option to share with sound.
Okay, so let me do that now.
Should be in the lower left. There should be a button.
I got it.
Thank you. Thank you. Okay.
Right. So I.
Now we can hear.
It's okay now. Oh.
The human body is made up of elements. There is oxygen in the lungs, carbon in our muscles, calcium in our bones, and iron in our blood. But the question is, where did these elements come from and how were they created? When I take a look at things around us, like plants, stones, and even the air we breathe, I see that they're made from the same elements as of humans. So does this mean everything in the universe came from the same thing? Yes, we are all connected, from the tiniest to the largest. We are made from stars, but what are stars?
So a star is a static hydrogen bomb.
Stars are always going under nuclear fusion at very high temperature and pressure. Lots of nuclei easily collide during this process as it is millions of degrees hot. The strong nuclear force binds them together to form elements like helium, carbon, oxygen, up to element number 26, iron. During nuclear fusion, stars get their energy to shine. Nuclear fusion is very important to us. If it wasn't for nuclear fusion, we wouldn't have water and everything around us, even sunlight during the day, as it is produced by our closest star, the sun. When the star dies, all elements formed are blasted into space as stardust. This stardust is what we are made from. We are stardust. Every atom of our DNA is stardust. Every atom in our skins, bones, blood is stardust. Stars produce elements during nuclear fusion, but the mass of the star determines how rapid it produces elements. A star that is less massive or equal to the mass of the sun produces elements very slowly, but a massive star that is a very high temperature and pressure, nuclear fusion happens very rapid. It produces elements very fast. The lifetime of a star is determined by the rate of nuclear fusion reaction, how rapid it is happening. For a less massive star, nuclear fusion is much slower. The star lives longer. There is an inverse relationship between the lifetime of a star and its mass. The higher the mass, the shorter the lifetime. Our sun is likely to live for 10 billion years, but less massive stars than our sun can live up to 100 billion years or even trillion years. So you say that light is the only material connection that we have to the stars, and we can use light to study the properties of stars. My question is, how do you use light to study the properties of stars?
When we go to a telescope, we are taking the light of stars and we point the telescope towards the stars that we are interested in. We collect their light, and inside, once the telescope only takes the light and focuses it, collects it. After we collect it, what we do with that light depends on something called an instrument. A telescope has an instrument connected to it. That instrument could be a camera, it could be a spectrograph. That means it could take pictures, or it can take the light and break it up into the colors of the rainbow. So I do both kinds of measurements, but in both cases, we are taking the light and we are trying to understand some set of properties of the star from which the light came.
From the light captured in the telescope, astronomers can learn how fast the star is moving, its chemical composition, its pressure and temperature. Light is very important as it is the only material connection we have to the stars. Our culture is directly connected to the stars. Most dances, designs, and religious practices are inspired by stars and their movement, also by the moon and the Milky Way. By merely looking at the movement of stars, we can predict the following years whether there will be hunger or not. Also, stars give us some other information.
Stars tell us how advanced the night is. You can tell without a watch. You can tell, you see a star that we call the morning star. It's called Venus. Once you see that one, it's called Indonsagusa in Ndebele. In other words, Ugusa means sunrise. So it pulls sunrise, literally, that's what we are saying. So that's the star which gives time.
There are a lot of designs that have been inspired by celestial bodies and the Milky Way.
When you look at the designs, the African designs, there is one which is informed by the Milky Way. The Milky Way has 4 arms. When you look at the design, decorative design on a Ndebele basket, now do you see what they've done? There's that arm and this arm and this arm, right? And when you look at them, do you see there are 4 of them? That the Milky Way has 4 arms. The solar system is a tiny blob here on one of them. But the Tonga women and Ndebele women produce this as decorative designs. This is the Milky Way.
By looking at the disposition of the moon, we can also get information about upcoming disasters like diseases.
Sometimes the moon is like this. When it's like this cupped, you know it means diseases. When it's like this opening, it's sort of emptying diseases. So they look at the disposition, the position of the moon, and then they can tell there will be diseases. This is why they think moon has the power to remove diseases. So hamba lo mkhuhlane, take away the disease.
In our culture, the moon also plays a vital role in rituals, but
there is no power. The traditional healers do not work when there is no moon. That among the Lozi many years ago, what they would do, they would have some kind of instrument called Ziso, which they used to monitor the coming of the new moon on the western sky.
Eclipse occurs when a portion of the earth is engulfed in a shadow cast by the moon, which is fully or partially
is seen as the sun, symbolized as the sun. So once upon a time, when there was Inwala ceremony, certainly there was a solar eclipse. Some of the soldiers were there, ran away, because the king got frightened. He is the sun. So when the sun rots, because they see it as rotting, and understanding of lunar eclipse and solar eclipse. So when there is a solar eclipse, it's disaster. Disaster.
In our culture, stars hold great significance as a lot of activities are determined by stars. Also, it is believed that we come from stars, and when we die, we also return to stars. Mom, what are those tiny, shiny dots that appear in the sky at night? And why do they only appear at night? Those are some of the questions I used to ask my mother whenever we were cooking outside when there was no electricity. In my hometown where I grew up, electrical cuts are very common. So we would go outside and cook using firewood. It will be very dark as there will be no artificial lights. I'll sit down, stare at the sky, and start wondering, what are those tiny, shiny dots called? Why do they only appear at night? How were they created and when? The only answer I could get was that they were called stars. Nothing else. All the other questions remained questions without answers. One day, when I was 13, staring at the sky, I saw a milky band of light. I was so fascinated and curious to know more about what it was. I went out, asking people what it was, but I never got answers. Only until one day, reading a book about the universe, I got to know that it was the Milky Way galaxy, and this is where we live. I also found out that stars don't only shine at night, but there's a star that shines during the day. The star is called the sun. This is the closest star to us. Light only takes 8 minutes to travel from the sun to us. But from all the other stars that we see at night in the sky, light takes 4 light years to travel to us. And the light that we see being emitted by the stars was produced millions of years ago. Most of those tiny, shiny stars that we see at night in the sky have lived for billions of years. We are way smaller than the stars. Upon knowing this, I felt very small, yet honored, as I was connected to the stars, since we are made from stardust. Stars are the raw materials of life. Whenever I look up in the sky, I don't only see shiny, tiny dots, but I see life.
That is such a beautiful video. Thank you, Knowledge, for sharing that. Thank you, Ru, for putting this together. And I know, Noku, you did something similar as well with your time at Santa Cruz. That was really fantastic. I also want to acknowledge the contribution of their mentor, Annette Lee, who really helped with putting everything together, the different parts of the story, helping the students put the story together. Thank you for sharing that. That was really beautiful. Amanda has gone to get a sandwich, but please feel free to ask questions and she will be back very soon. I'm going to connect my laptop to the power source here so it doesn't run out of battery. I'll be right back. 1 second. Okay, I'm ready for your questions. Any questions at all, please?
If there is anyone raise up your hand or if it's the mic, you can ask. All right, for now, basically.
Any questions from the classroom?
This is Arare. The students are saying there's no one with this question. That's we have got one. Okay, great. We have got one.
Good afternoon.
Good afternoon.
I noticed that all of you mentioned that when you're observing stars, there would be something particular that you're looking for. So I wanted to ask, what are some of the things that you look for when you're observing the stars? Is there anything in particular that you would be searching for?
That's an excellent question. Thank you.
Exposure complete.
So we are looking for at least 3 things when we take the spectrum of an object. First of all, when we take a spectrum, you'll see that its spectrum will appear here in a few seconds. Before we take a spectrum, we don't know what it is. We think it may be a star in Triangulum, but sometimes we could be wrong. It's like saying, I walk into a grocery store, but unless I open the packaging, unless I taste the food, I don't know whether it's the right kind of food for me. So just the same way, unless we take the star and before we take its spectrum, we don't even know if it's a star. Sometimes what we think is a star may be a galaxy or a quasar in the background.
Readout complete.
You'll see this appear in just a second. There we go. Sometimes we see that what we thought was a point of light is really a collection of stars in the background, a galaxy or a quasar. Sometimes we see that it's a foreground star in our own Milky Way, not in Triangulum. So that's the first thing we're trying to understand from the spectrum is, what is it? Is it a star in Triangulum or is it something else? Once we know the answer to that, from the spectrum, we can determine the answer. Then we are interested in 2 more questions. How fast is the star moving? And we can actually answer that question even if it's not a Triangulum star, even if it's a star in the Milky Way, we can answer the question of how much Doppler shift does it have on the spectrum. And even if it's a background galaxy, we can answer the question, how much Doppler shift does it have? And that tells us how fast the thing is moving. The third thing we can answer is what kind of chemical composition and what properties it has on the surface. What is the temperature of the star? What is its chemical composition? And those are the 3 things. Whether it's a star in Andromeda, whether it's a star in Triangulum is the first question, yes or no. 2, what is the velocity? 3, what are the properties of the star in terms of temperature and gravity or pressure and chemical composition? Those are the 3 things we are trying to, 3 broad questions we're trying to answer. That was a very good question. Tell me your name again, please.
Nicole.
Say that again, please.
Nicole.
Nicole, okay, thank you. That was a great question. Which grade are you in?
I'm currently doing lower 6.
Okay, okay, thank you. Thank you very much for your question. Did I answer it properly?
Yes, you did. Thank you.
Okay, thanks.
Everyone?
For another student with a question, she's coming through.
Thank you.
I wanted to ask, you said, I saw that in Ruth's video, that a star has to explode, and when a star exploded, that life was created. So, have you ever observed other stars exploding in the Triangulum? And if so, is there any proof of life that has been created from that explosion?
That's an excellent question. Stars do explode. We have not seen any star in the act of exploding in the Triangulum galaxy. What we can see is after the explosion, what is left behind for certain stars. We can see what are called supernova remnants. A supernova is what the name given to an exploding star. We can see the after effects of the explosion in Triangulum, and we can see stars that we think will explode in the future. But human lifetime is very short compared to the lifetimes of stars. So it is very rare for us to catch an exploding star in general. And we have not, at least I have not seen any exploding star in Triangulum, but I've seen exploding stars in other galaxies, and my colleagues have seen exploding stars in other galaxies. So we don't have any direct evidence of life in the Triangulum galaxy. We don't, but we can see that the same elements that we see here on Earth, like carbon, nitrogen, oxygen, iron, all of these elements, we can see their presence in the Triangulum galaxy. Specifically, we see sulfur, nitrogen, oxygen, carbon, of course, hydrogen and helium. We see evidence of these elements in the stars in Triangulum, very much like the elements present in the sun.
Thank you.
Thank you very much for your question. That was an excellent question. I should say that our sun is not going to explode. It's not massive enough to explode. A star has to be something like 3 or 5 times the mass of the sun for it to end its life in an explosion. Our sun is going to end its life in a much more quiet way. It will grow bigger and then it will shrink, but it won't explode.
Good afternoon.
Good afternoon.
I heard you say that the Triangulum galaxy is 3 million years away. But how do you identify the amount of years that separates another galaxy from us?
Could you repeat your question, please? I couldn't hear very clearly. Could you repeat?
How do you identify the amount of years that separates another galaxy from us?
How do we identify whether the star we are looking at is from Triangulum? Was that your question?
No. How do we know that it's that amount of years? Like, for example, the Triangulum galaxy is 3 million years away. How do you know that?
I'm still having some difficulty with the audio. Could you understand?
No, the important part of your question cuts out. We hear the lead up and then how do we know that, but not your question.
Yeah, so what about the Triangulum galaxy are you asking the question about? How do we know its distance?
Yes.
That's a very good question. How do we know its distance? The way we know distances to galaxies is using something called standard candles. I'll explain what I mean by that. Other astronomers, long before Amanda and I started studying Triangulum, they found certain classes of stars that they could identify how powerful these stars were, how much light they were putting out. There was a class of stars called Cepheids. I'll put the name in the chat, Cepheid variables. I'll temporarily open up the chat. These are stars whose brightness varies in a characteristic way. And a very famous astronomer named Edwin Hubble, and before him, several astronomers, including Cecilia Payne at Harvard Observatory, they figured out exactly how powerful these stars are. Once you know how powerful it is, and you see this star, that kind of star, in a galaxy, from the apparent brightness, you can figure out how far away the galaxy is. So it's like saying, if I know my neighbor has a 100-watt light bulb in their backyard, and I'm walking, or in my house has a 100-watt light bulb in the backyard, when I'm walking home from school and it's dark, I can tell how far away I am from home just by seeing how bright that light appears to be. When I'm getting close to home, that light will look very bright. When I'm far away from home, the same light will look faint because I'm far away. So we use that method to figure out how far away a galaxy is. That's one of the methods we use to determine how far away a galaxy is. We first have to know the power of the star, and we know that through other associated properties of the star. In the case of Cepheid variables, we know that from the fact that they pulse up and down in brightness, but we know their power. And once we have identified such stars, we can figure out the distance. Did I answer that question? Did you, was that clear?
Yes, you did. Thank you.
Thank you very much for your question. And I'm sorry that the audio prevented us from hearing it the first time. Thank you for asking.
Anyone?
Amanda, this one is even better than the first in terms of stars. Lots of things on the mask.
Just playing around with it.
Hi, hello.
My question is directly on the screen about those rectangular pieces, those light pieces, if I'm correct. I want to ask how suppose a reactor is passing through triangular M33. This does it show an irregularity on that phasor?
What about the spectrum? Again, we're having some difficulty with the audio. Sorry.
My question is about suppose a UFO is passing through triangular M33. Does it show a irregularity of a light spectrum?
I could hear the word spectrum, and are you talking about the spectrum that my cursor is pointing at right now?
Yes.
Okay. Any particular spectrum or particular aspect, like these lines over here that are horizontal, or the vertical lines?
I'm asking about suppose a UFO is passing through.
So I have never seen a UFO. So but what happens occasionally is when we are taking not a spectrum, but when we're taking an image of the sky, we will see a streak of light because the object is moving. And typically, it's not a UFO, but typically it's a satellite that is going around, that's going around the Earth. So it's a piece of metal, like a rocket that's going around the Earth. And we can see the sunlight that is reflecting off that satellite. If it could be the International Space Station, it could be the Hubble Space Telescope, it could be some other kind of satellite that either the NASA has sent up or some other space agency of another country has sent up. So we will occasionally see that when we're taking images. That is, if we're taking a 5-minute image during that time, the object is moving in the sky and we see a line of light across that. I have seen that happen quite often when we're taking images, not so much when we're taking spectra. Thank you. Thank you for your question. I'm sorry, again, it was difficult for the audio to pick up your question initially. But thank you for asking.
Hello, Raja.
Hello. Hello.
Hello. Yeah, so it's now about 10 minutes to 3 p.m. this site. And the students will need to travel. But before they go, we need to do some good photos that we can share some of them on social media. So I will be doing some photos right now, and then within 10 minutes, I think the students will be leaving.
Okay, what I'm going to do is I'm going to make you the primary video. I'm going to spotlight your video for everyone. So when you get together for a group photo, hopefully the camera will also pick it up and we'll be able to see it over here. But this is our clearest view we have so far of the classroom. And it's so wonderful to see so many students gathered here for today's event. And Knowledge, thank you for making this happen. It's really fantastic.
Oh, thank you, Raja. So yes, we'll be doing group photo. So
Yeah, we are almost done this session. So we are ready to get I think I'm not sure.
Now, I realize it's winter right now in Zimbabwe. Is it very cold outside? I see many of you are wearing your blazers and school uniform. Is it cold right now?
Oh, it's so we allow some.
This reminds me so much of my school days. We had to wear a school uniform when I went to school. You didn't have a school uniform in school days?
I did at the very beginning.
I see.
Because there was no public preschool and kindergarten in Georgia. So I went to a private one and had to wear a uniform.
Knowledge, please let me know when I should stop the recording. For now, we are continuing the recording, but let me know when you'd like me to stop.
Yeah, we are done with the group photos.
Okay. I know it is exactly 3 o'clock, and I know that we had planned to stop right at 3. So, any closing remarks from you, Knowledge? And again, I just thank you so much. I know how logistically how difficult it is to put an event together like this. So, thank you for making this happen.
We should thank you, Raja, and the team for this opportunity. Thank you for the great you STEM education. And I hope we will see more students from Zimbabwe and other parts of Africa applying to the SEED program. For the observing sessions in October, we are going to join with more schools. So thank you very much. I think that's what I can say.
Thank you. In the October sessions, I know we'll be using a different telescope. We'll be using a telescope in California, not Hawaii, for 2 of the nights. One of the nights will be on this telescope, but 2 of the nights will be in a California telescope. But I'm looking forward to that. I've got that on my calendar as well. That's in early October. I think we're using the California telescope.
Thank you so much. What is teaching in Hawaii?
What was that, Knowledge? Say that again, please.
That's one thing I was asking about the time. What time is it in Hawaii? Is it 3 a.m. or?
Yes.
It is 3 a.m. now in Hawaii, exactly. It is exactly 12 hours earlier than Harare. Middle of the night.
I should say that we will be leaving the war now, and we hope to join you in the session, in October sessions.
Looking forward to it.
Good night for all of us.
Thank you. Good afternoon to all of you. Bye.
Bye.
Okay. So thank you so much for coming. And that we have learned a lot. There's so much more to learn with those sessions. So we should join some of those sessions. Managed to see some of those spectra and then from there. Okay. Thank you, Ms. At this moment, I would also want to acknowledge the presence of Elizabeth and Dr. Thank you for joining us.
Thank you very much. Thank you. You're most welcome, and thank you. Thank you for the excellent questions. Thank you for all the attention you've given us.
Genesis.
All right.